Okay, awesome. We'll introduce our speaker now that we're very happy to have here. He is an assistant professor in statistics from Colorado State University. He received his PhD in statistics from UT Austin, so very close to home, in 2017, and with an honorable mention from the Savage Award for Outstanding Dissertation. And he went on to postdoc at North Shore University Health System and the University of Chicago under Dr. Yuan Ji. And his lab has been focused on developing Bayesian statistical methods and computational tools for dealing with missing data and the characterization of tumor heterogeneity and designing clinical trials in an oncology setting. And so, but they have also shifted to working on COVID and published a package, BaySIR, to infer the speed of COVID-19 spread and the effects of mitigation policy. And that was from a while ago. So I'm very excited to see what he's going to discuss today and maybe update on his work. And we'll learn some cool things about statistics. So please join me in welcoming Dr. Tianjian Zhou.
Yeah, thank you, Emily, for the kind introduction. It's a very honored to be here to join the discussion group and also to present some of my research on COVID. So maybe I'll share my screen then. If you cannot see my screen, just let me know, but I guess it should pop up. Cool.
Yeah, we can see it.
Great. So as Emily mentioned before, I got my PhD in statistics from UT, so it's great to be back. And my PhD advisor, Peter Mueller, is actually in the audience. So very, very happy to meet everyone here. And also, I would like to mention that my primary research area is in clinical trials now, but I have also been working on Bayesian semiparametric and non-parametric methods. So when the pandemic began, I was really interested in seeing how this research about inferring the transmission dynamics of COVID works, and I was motivated to contribute to this area using my expertise. So this work has been published in the journal Contemporary Clinical Trials. If you are interested, feel free to check that out. And in that paper, we focused on two goals. The first goal is the retrospective estimation of the epidemiological parameters of COVID-19, such as its effective reproduction number. And the second goal was to predict the future case counts, which I think is a challenging task, and caution is needed when we try to do such a prediction. So these two figures below illustrate the two goals. The first figure here shows the estimated time variant effective reproduction number of COVID in Illinois. And the second figure here shows the predicted number of cases back in 2020. Of course, now we know the truth, what the truth is, and you will see that the predictions were somewhat off, but that's due to the challenging nature of this task. And I will briefly describe how we achieve these two goals. There are many ways to achieve these two goals, but for us, we took a compartmental modeling approach. So before that, I would like to give a brief review of what a compartmental model means. I believe many of you may be very familiar with that, so I'll be pretty fast. A compartmental model divides a closed population into compartments, which correspond to different stages of a disease. For example, consider the picture on the right-hand side. Suppose there is a closed population, meaning that we ignore immigrations, etc. And most of the people at the beginning may not have a disease, so they are characterized by this state of no disease. Some people have the disease, and some people may have already been recovered from the disease, so they cannot So by assumption, they are immune from the disease and they do not participate in the transmission dynamics anymore. We assume that individuals in the same compartment have the same characteristics, and we are interested in how these individuals flow through these compartments over time. And the flow of individuals through compartments characterizes the dynamics of the spread of the disease. As you can imagine, if these people without the disease become people with
Dr.
disease
Zhou,
pretty
I'm not
fast.
sure if we're seeing the slide you want to show. Maybe
okay.
we just see review of compartmental models for epidemics.
Oh, okay. Let me reshare this to optimize sharing the
Thank you
screen.
so much. Sorry for
Yes.
interrupting you.
Yeah, no problem. Thank you for mentioning that.
That looks great. Thank you.
Okay, cool. And as you can imagine, if those people without the disease become people with disease pretty fast, then that means the spread of the disease is pretty fast. And we need to be cautious now. So the classical SIR model considers a partition of the population into 3 compartments. The first compartment is called the susceptible individuals who do not have the disease and can be infected. The second compartment consists of those with the disease and can infect others. And finally, the third compartment consists of those who had the disease before, but then were removed from the possibility of being infected again or spreading the disease. So in the classical SIR model, the transmission dynamics of the disease can be characterized using the diagram here on the top of the slide. Let N denote the total population size and the characterization of the flow of individuals through these 3 compartments can be done using a set of differential equations. And in this case, we have 3 compartments and their population sizes can be characterized using 3 differential equations. And I'll briefly introduce the intuition behind these differential equations next. The trajectory of the disease is fully determined by the initial values of these differential equations and parameters. As an example, suppose the initial population sizes of 3 compartments are, say, 500 and say 1 and 0 for the S, I, and R compartments. And given some fixed transmission rate, then we can solve the system of differential equations and get these 3 trajectories. The rationale behind these differential equations is as follows. First, we assume that each infectious individual makes effective contacts, which are sufficient for disease transmission with beta others per unit time. And of course, some of these effective contacts are with the removed individuals. Some of these are with the infectious individuals who have already been infected. So only these contacts with susceptible individuals are capable of transmitting the disease. So we get a factor of beta multiplied by S divided by N here. And in total, we have I infectious individuals, which leads to a rate of new infections being beta SI divided by N. So that's the rationale of the first differential equation. The second differential equation is much easier to understand. We assume that the infectious individuals leave the infective class at a rate of alpha I. They can recover, for example, or they may die. As a result, they no longer participate in the transmission of the disease. So here we can introduce some terminologies. The beta parameter is known as the disease transmission rate. It characterizes the speed of disease transmission, and there is a major interest for us to infer this parameter for COVID-19. Alpha is known as the removal rate, and the inverse of that is known as the infectious period. And finally, we have this basic reproduction number, which is defined as beta divided by alpha in a standard SIR model. We also have the so-called effective reproduction number, which is given by beta S0. S0 is the initial size of the susceptible population. divided by alpha times n, where n is the total population size. So this number has some important clinical implications. If this number is less than or equal to 1, then the population of infected individuals will decrease monotonically to 0, meaning that the spread of the disease has been effectively contained. In our case, if we can control the effective reproduction number of COVID-19 to be below 1, then that means we are nicely containing this disease. However, if this parameter is greater than 1, then the population of infectious individuals will increase. But of course, eventually it will decrease to 0 because eventually all people will be recovered from the disease. Sometimes for computational issues or for simplicity, people often approximate this system of differential equations using a discrete time model. The rationale is pretty similar, but the only difference is that we replace these continuous trajectories by these discrete time approximations. So that's a brief introduction of the simple SIR model, which again, I assume most of you will be pretty familiar with. But we can make a few extensions to the SIR model, especially for COVID-19, which can make the model more realistic. The first issue is that we should account for randomness in disease transmission and observations. As we know, the conventional SIR model is a deterministic model, which is usually employed by mathematicians. They assume the disease transmission rate is a given number, and then they can simulate the trajectory of the disease. From there, we can see how severe this disease can be. But to formally estimate these parameters and to quantify the uncertainties in the parameter estimates, we should take some statistical approach. The second extension we can make is to add more compartments so that the model is more realistic. And we'll see more of that later. The third possible extension is that we can add vital dynamics, demographic information, and more possible transitions among the compartments. And finally, we might allow this compartmental model to have time-varying parameters. Specifically for COVID-19, we would expect the transmission rate of that will change over time and also potentially be affected by mitigation policies and possibly other covariates. So in our extension, we considered 3 of these extensions, and we will see more of that later. So now I'll briefly go over the proposed state space model for COVID-19 with a package which is available on GitHub. So if you're interested, you can go to that link and try that package. For me, I haven't updated the results for a while because I did this research last year. So I didn't really keep track of that for the transmission dynamics this year. But again, if you're interested, you can try that yourself. For modeling COVID-19, again, I consider several simplifying assumptions. We consider a specific region, and we consider a closed population by ignoring immigration and emigration. I would say these approximations are okay for a fast spreading disease like COVID-19. As I mentioned before, we might increase the number of components to better capture the nature of the disease. Specifically for COVID-19, the extension that I did is to break down the infectious compartment into 2 different compartments. The first one is called the undocumented infectious individuals. As we know, for COVID-19, a lot of transmissions happen before an individual is diagnosed with the disease. In other words, when they are undocumented at the undocumented infectious state. Of course, many of these people who had COVID-19 are documented, especially if they are symptomatic, then they will go and get a test and then they become documented. And finally, there is a removed class. The transmission dynamics is again captured by a set of equations, but here with one more compartment here. The assumptions is that on a specific day, suppose that each infectious individual, either undocumented or documented, makes effective contacts with beta T others. And based on the same rationale, a portion of these contacts are with susceptibles, thus can make the transmission of the disease happen. A fraction alpha of infectious individuals are removed from the infective class. And finally, a fraction of undocumented infectious individuals who have not been removed yet are diagnosed with the disease. So based on these assumptions, we can write out the system of equations for the transmission dynamics of COVID-19. Of course, that's a simplification of the real process, but I would say it still provides insights to the transmission dynamics of COVID-19. Here in this equation, actually a lot of parameters are unobserved. The only thing that is observed in this set of equations is this one, which is the daily confirmed cases. And we can denote this number by BT minus 1. The other things are all latent and unobserved. And here, beta is the parameter, alpha is the removal rate, which is another parameter, and gamma is the detection rate, which is yet another parameter. But it looks like these equations have a lot of parameters and latent observations, but still the epidemic process is fully determined by the initial values, the parameters, and the observations. So these are the things that we are trying to infer using a statistical model. For this model, the effective reproduction number at time t is defined as beta t st divided by alpha times n. This is similar to the effective reproduction number that I defined before for the simple SIR model, but with the time varying parameters, this effective reproduction number is also time varying. And the interpretation also slightly differs from the classical SIR model. It means the rate of secondary infections generated by each infectious case at time t at a specific time t, scaled by the length of the infectious period, alpha inverse. But still, this parameter characterizes the speed of disease spread at time t. And again, this parameter, if is lower than 1 after time t, then it indicates containment of the disease. So here comes the statistical model. I used a logistic regression model for the diagnosis rate. Remember that gamma t is the diagnosis rate. We consider the logit of gamma t, and we model that using a linear regression model. So here, essentially, we can put covariates here, like the number of tests, for example. In practice, I found out using this simple model specification, it's pretty hard to infer these regression coefficients if we put a lot of covariates in. So for simplicity, in my early work, I only used a constant mean logit diagnosis rate. But that framework can potentially accommodate more covariates, as we will see in the last few slides. And taking a Bayesian approach, I also specify the priors on the latent parameters. The other unknowns include the initial condition, which I put some other priors again. Another parameter, important parameter, is the transmission rate, which I consider the log of the transmission rate because it has to be strictly positive. And then I put a Gaussian process prior on the transmission rate. That's where the Bayesian semi-parametric method comes from. The good thing about the Gaussian process model is that we don't have to assume a specific parametric form of the transmission rate. For example, from the picture on the right-hand side, we can see the curve can be pretty say it can be non-monotonic. For example, it doesn't have to be linear, either in the log scale or in some other scale. So that's the flexibility that a Gaussian process model can give. And finally, I put another gamma prior on the removal rate. You can see that I did put a lot of informative trials on the parameters. And the reason why I'm doing that is because for the model that I mentioned before, the parameters are essentially unidentifiable with only daily confirmed cases observed, which is expected because as if you still remember, the model looks like it has a lot of parameters, but only one of them is observed. And it is indeed the case that a lot of them are unidentifiable. As an example, here, these two different epidemic processes given in the two pictures here with different transmission rate and different effective reproduction numbers can give exactly the same observations, which is the daily confirmed cases here. So I have to put some informative trials on some parameters to make this problem identifiable. And these trials may be elicited from clinical results from the natural history of COVID-19. So extra information is possible. So again, these are the parameters that we are inferring, and we have some hyperparameters. I used Markov chain Monte Carlo algorithm with Gibbs and Metropolis Hastings updates to draw samples from their posterior distributions. So if you're interested in more details, Peter Mueller is an expert on this. So I conducted several simulation studies. These are the generated hypothetical epidemic trajectories, which I think mimic the daily number of cases of COVID-19 in some regions. Although, in my opinion, these curves look pretty similar, but actually the effective reproduction numbers behave slightly differently in these three cases. In case one, the effective reproduction number decreases monotonically to 0. In the second case, it is non-monotonic, and in the third case, it decreases like a step function. But in all the three cases, our model, the result given by our model is illustrated using the solid black curve here. And the red dashed line shows the simulation truth. We can see that in all the cases, the truth is recovered pretty nicely. So we applied this method to infer the effective reproduction number for several states in the United States. And these are the results. The vertical dashed line shows the start date of the stay-at-home order, and the second vertical dashed line shows the start date of the relaxation of the stay-at-home orders. We can see there seems to be some relationship between the mitigation policies and the decrease of the effective reproduction number. So although this relationship is not characterized in a formal way, but we kind of see there is some correlation here. But later I will show you how to incorporate this information in a more formal way briefly. Another way, remember that our second goal is to make predictions for future case counts, and that's our results. We can see the predictions are pretty off, I would say. But that's not totally unreasonable because the gray shaded area shows the uncertainty interval or the posterior credible interval. We can see our predictions have a huge uncertainty, so in that sense, the observations are still covered by the credible intervals, but we can see the posterior mean is pretty off. I would say that such predictions are based on extrapolation of the current trend. And we know that extrapolation is not good in a linear regression, for example, which makes our prediction not very reliable. So if the current trend of disease transmission changes, then prediction is inaccurate. But for COVID-19, the trend changed many times, I would say. And actually human behaviors are highly unpredictable. So even though the Gaussian process model predicts that that's the trend of the effective reproduction number, due to human behaviors, it can as well increase in a very fast rate if we say release these mitigation policies. So I would say caution is needed in interpreting the prediction results, but nevertheless, this is a framework that we might employ to make predictions. So there are some future works that can possibly be done. For example, we may use a hierarchical model that models multiple regions jointly. So currently in my previous work, I did them separately. In other words, when I model the transmission of COVID in Colorado, I didn't take into account the information at Texas, but potentially that can be done. We can include other compartments like those who have been exposed to COVID-19 but are not yet infectious, those who are hospitalized, etc. We may think of better use of covariates. So now in my previous work, I actually didn't use any covariates, although I did provide a framework for using covariates. And finally, we may think of sequential Monte Carlo, which can increase the speed of posterior sampling. But actually, recently, we did implement two of these extensions, and I'd like to show you some results. So this is another work that I recently done with my colleagues at Colorado State University, in which we did consider a better extension of the previous model, which you can see that there is an exposed compartment. There is a recovered, we separately model the number of recovered cases and the number of deaths. And there are other changes, other refinements to the previous model, but I'm not going to talk much about the details due to time constraint. A good thing about this model is that we now explicitly consider how the population mobility of people can impact the transmission dynamics of COVID-19. And this figure is an illustration of the population mobility for several kinds of activities at Colorado. So these data are available on a web page called SafeGraph, and I believe many of you will also be familiar with that. So after incorporating this information in that model, we can explicitly see the contribution of mobility to the transmission rate, to the disease transmission rate. So there are three types of mobility data, and these are the coefficients, the regression coefficients. And you can imagine them as the regression coefficients of these mobility data to the disease transmission rate. And these horizontal bars shows the posterior credible interval, and these dots show the posterior means of these coefficients. So the scale of these coefficients really don't matter here, but we can see some of these are significantly different from zero, meaning that we do see a contribution of mobility to the transmission rate. With more people working full time, the transmission rate gets higher. But of course, we also see that for some states or counties, this parameter is either negative or covers zero. So there's a question asking, are these estimates obtained separately as well? The answer is yes. And a future topic is, of course, to model these, to estimate these parameters jointly. By modeling them separately, I mean that we are modeling for each state and county separately, but these three parameters are included in the same model. But I was talking that some of these coefficients either are negative, which is counterintuitive, or they are not significantly different from zero. But that can potentially be due to the collinearity between among these three measures. So again, when we interpret these results, some cautions are needed. So that's all. And feel free to let me know if you have any questions, and feel free to check these papers out. And you can also contact me through email afterwards. Thank you.